And I'm Lucas, and we're going to be measuring the effect of adenosine, antidiuretic hormone, known as ADH, and histamine on the flow of fluid through the blood vessels and across the capillary walls of a frog. To set up this experiment, a Ringer's dextran 3% control solution was prepared along with a 2 millimolar adenosine, 1 microgram per milliliter ADH, and 1 millimolar histamine solution. To prepare the frog, the skin was removed from the frog and an incision was made from the lower abdomen to the neck. We then cut across the ribs to expose the heart. All the internal organs and extra tissue and bones were removed except for the heart, aorta, lungs, and kidneys. We then inserted a catheter filled with Ringer's dextran solution into the left branch of the aorta. The transducer was calibrated by adding weights in 10 grams increments until a total of 50 grams was reached. The lowest transducer output value for each added weight increment was plotted against its corresponding weight value, eliciting this calibration curve. A linear regression was observed giving the calibration equation weight in grams equals 0.1841 grams per millivolts times transducer output in millimoles with the y-intercept of 75.518 grams. The y-intercept value was removed from the calibration equation because the offset knob was adjusted in the beginning of the lab. The frog was then hung from the transducer from its lower jaw. The ventricle was cut to allow outflow so that the drip rate could be calculated. The funnel filled with Ringer's dextran solution was adjusted to be placed at a position 24 cm above the level of the frog's heart, and the solution was allowed to perfuse the frog. Weight recordings were obtained using chart in order to calculate the change in weight rate. For each weight recording, the vertical axis was adjusted to reflect values of weight in grams. This was done using the calibration equation we found. A linear regression line was added to reflect the baseline slope. The change in time was found by taking the difference in the time values, whereas the change in weight was found by taking the difference in the weight values. The change in weight rate was then found by taking the slope of the baseline, which was calculated by dividing the change in weight by the change in time.
The change in frog's weight can be explained using Starling's equation of ultrafiltration. This equation calculates the magnitude and direction of water flow across the capillary wall. Flux depends on the capillary blood pressure, the interstitial tissue pressure, capillary blood oncotic pressure, and interstitial oncotic pressure. The forces that push water out of the capillary depend on the capillary blood pressure and the interstitial oncotic pressure that leads to filtration. The forces that push water into the capillary depends on the interstitial tissue pressure and the capillary blood oncotic pressure. This leads to absorption. A positive flux leads to filtrations, whereas a negative flux leads to absorption. Filtration causes water to flow from the capillary to tissue, and absorption causes water to flow from the tissues to the capillary. Weight gain is a result of water accumulating in the tissues, while weight loss is a result of water leaving the tissues. Poiseuille's law is used to calculate the resistance of flow through a tube and is proportional to nu, which represents the viscosity of the fluid and the length of the tube and is inversely proportional to the radius of the tube. Ohm's law can be used to measure the flow through a tube. Flow, which is represented by Q, is proportional to the pressure difference along the tube and is inversely proportional to the resistance of flow. An increase in flow causes an increase in drip rate, whereas a decrease in flow causes a decrease in drip rate.
Adenosine is a purine found in the body that can cause dilation of blood vessels, enhancing the blood supply to muscle tissues. From this, we expect vasodilation, which would lead to an increase in both the change in weight and the drip rate. ADH can be a vasopressin, and is used to treat over-dilated blood vessels. So we expect for the arterioles to constrict, causing a decrease in both the change of weight and the drip rate. Histamine is released by the body during an immune response when a foreign substance is sensed. This causes inflammation, so we expect histamine to cause vasodilation of arterioles, resulting in an increase in both the change in weight and the drip rate.
Adenosine. In our experiment, the drip rate was increased to 44 drips per minute and the change in weight rate was increased to 0.00036 grams per second. Adenosine starts by binding to either adenosine 1, also known as adrenergic alpha-1 receptor, or adenosine 2, also known as adrenergic beta-2 receptor. Binding to adrenergic alpha-1 receptors results in muscle contraction, but in this experiment, more adrenergic beta-2 receptors were present. Upon binding to the adrenergic beta-2 receptor, the corresponding GS protein is activated, stimulating adenylyl cyclase, which converts ATP to cyclic AMP, abbreviated CAMP. CAMP activates protein kinase A, denoted PKA. PKA inhibits the ryanodine receptors on the sarcoplasmic reticulum and L-type calcium channels on the membrane, but activates the potassium channels. By inactivating RYR1, calcium is no longer able to flow from the sarcoplasmic reticulum to the cytosol. Inactivation of L-type calcium channels prevents the flow of calcium ions into the cell. Activating potassium channels allow potassium ions to flow out of the cell, causing a decrease in positive charge intracellularly. This allows for positive sodium ions to flow into the cell, which calcium is coupled and pumped against its concentration gradient by the sodium-calcium exchanger. The decrease in cytosolic calcium concentration causes calcium ions to unbind from calmodulin. PKA will activate myosin light chain phosphatases and inhibit myosin light chain kinases. By activating myosin light chain phosphatases, the phosphate groups are removed from the myosin heads, inactivating them. This results in no cross-bridge cycle, so tension cannot be generated. This leads to smooth muscle relaxation, causing the blood vessels to dilate. More fluid flows through the blood vessels, increasing the capillary blood pressure. This causes an increase in flux. This means that net water flow is from the capillaries into the interstitial tissues, resulting in either a weight gain or an increase in the change in weight rate. Vasodilation of arterioles causes the radius of the arterioles to increase. This causes resistance to decrease. A decrease in resistance causes an increase in flow, resulting in a higher drip rate. Upon the addition of ADH, the drip rate was decreased to 36 drips per minute, and the change in weight was decreased to negative 0.00129 grams per second. ADH begins by binding to either the V1 or the V2 receptors. The V2 receptor would cause the smooth muscle surrounding the arterioles to relax, resulting in vasodilation of the blood vessels. However, in this experiment, more V1 receptors were present in the arterioles, which led to activation of the corresponding GQ protein. This leads to an activation of phospholamban C. PLC converts membrane phospholipids to diacylglycerol, abbreviated DAG, and IP3. DAG activates protein kinase C. PKC activates L-type calcium channels, which allows calcium to flow down their concentration gradient and into the cell. PKC also inhibits potassium channels, which prevents the efflux of positive ions outside the cell. This causes a decrease in sodium-calcium exchanger activity, so calcium is no longer pumped into the cell. IP3 goes to the sarcoplasmic reticulum and activates ryanodine 1, which allows the calcium stored in the sarcoplasmic reticulum to enter the cytosol. Cytosolic calcium ions then bind to calmodulin, forming a complex that will bind to caldesmon and actin, exposing the myosin binding sites. PKC will also activate myosin light chain kinases, which will phosphorylate the myosin heads and increase myosin ATPase activity. PKC will also inhibit myosin light chain phosphatase, which dephosphorylates the myosin heads. Through the activation of myosin light chain kinases, there will be an increase in cross-bridge cycle, causing the arterial smooth muscle to contract and vasoconstrict. Because ADH causes vasoconstriction, less fluid is able to flow through the blood vessels. This causes a decrease in flux. This means that net water flow is towards the capillaries, resulting in a weight loss or a decrease in change in weight rate. Vasoconstriction of arterioles causes the radius to decrease. This causes an increase in resistance. An increase in resistance causes a decrease in flow, meaning that drip rate will decrease as a result.
Upon the addition of histamine, the drip rate was increased to 40 drips per minute, and the change in weight rate was increased to 0.00122 grams per second. Histamine can bind to either H1 or H2 receptors. The H1 receptor results in smooth muscle contraction. However, in our experiment, there were more H2 receptors present on the arterioles. When histamine binds to H2 receptors, the corresponding GS protein is activated, stimulating adenyl cyclase. This results in the conversion of ATP to cyclic AMP. Then, the same cyclic AMP pathway that happened as a result of adenosine binding occurs. In addition, histamine causes the release of nitric oxide. Nitric oxide diffuses to the smooth muscle, activating guanylyl cyclase. This converts GTP to cyclic GMP. PKG can activate myosin light chain phosphatase and inactivate myosin light chain kinase, causing dephosphorylation of light chains on the myosin heads, so the cross-bridge cycle cannot be generated. Also, PKG inactivates L-type calcium channels, leading to a decrease in cytosolic calcium concentrations. This will cause calcium to unbind from caldesmon, resulting in tropomyosin recovering the myosin binding sites on actin, so tension cannot be generated, leading to further muscle relaxation and vasodilation of the arterioles. Because histamine causes vasodilation, more fluid can flow through the blood vessels and increase the capillary blood pressure. This causes flux to increase. This means that net water flow is out of the capillaries, resulting in weight gain or an increase in the change in weight rate. Additionally, vasodilation of arterioles causes the radius of the arterioles to increase. This causes resistance to decrease. From Ohm's law, a decrease in resistance causes an increase in flow, resulting in a higher drip rate. From this experiment, we learned that upon the addition of adenosine, there was an increase in both the drip rate and the change in weight rate. This means that flow through the blood vessels and across the capillary wall was increased as a result of vasodilation. ADH had the opposite effect, leading to a decrease in the drip rate and a change in weight. This occurred because of ADH's ability to constrict the arterioles. Lastly, histamine caused an increase in the drip rate and the change in rate, reflecting histamine's ability of vasodilation. With the knowledge of these drugs' effects, we can make practical implications that can be applied to medicine.
Thanks for watching.
Gracias por su atención.